Swayam Prabha. Digital India. Educated India.
So as I mentioned, the estimating, so in order for the generative classification to work well, it's important that we estimate the class conditional distribution reliably. So because if we do a bad job at estimating this distribution, then the overall results will suffer. Okay. So as I also mentioned, typically, if you're not careful with how you are representing this distribution, you may have to learn too many parameters in order to estimate this. For example, if we say that P of x given y is a Gaussian with full covariance matrix, then we have to estimate just too many parameters, right? So that's not an ideal thing to do. Okay. So there are many ways, like the naive assumption is one way to reduce the number of parameters. As I mentioned, estimating the class conditional P of x given y and the class marginal P of y can be either done using MLE, but MLE can overfit because there is no prior information. If you don't have enough data from each class, then you can overfit, right? So a map or a Bayesian approach which takes into account the prior information can help you basically dealing with overfitting. Okay, so essentially, like generative classification, it ultimately boils down to density estimation. You have to estimate the density P of y and density P of x given y. If you have done a good job there, your final generative classifier will be fairly accurate. Okay, and that makes it very flexible also, because there is a lot of work, recent work on designing like very strong generative models for data, right? Where you can learn, even if you don't have a lot of data, you can actually learn generative models fairly reliably. So any improvement on basically estimating the probability density of data, any significant advances will help generative classification as well. Okay, so we have given a very brief overview of probabilistic classification, focusing mainly on generative classification. As I said, I deliberately did not talk about discriminative classification because you have seen how logistic regression works in one of the previous lectures. All right, so moving on to the next topic. Yeah. Naive ways. Yeah. So even Gaussian classifiers, like, so I think many models like semi-supervised learning models, yeah, so they are all generative classification models. The discriminative classification model would not work in a semi-supervised setting because you don't have any way of incorporating the P of x, right? Yeah. So one of the reasons why generative classification models were not as popular is because they are hard to learn. Because you typically, because the reason is that estimating P of x given y, it's not easy, right? You have to make these simplifying assumptions, like naive ways, right? But when you make these simplifying assumptions, you are ignoring a lot of structure that may be there in the data, right? So,
such a big assumption.
Yeah, exactly, yes. Right. Yes. And the other thing is that typically if our goal is to do classification, people say that why care about modeling the x, right? Just directly model the y. And if you have plenty of training data, right, you would learn the P of y given x anyway, even if you just use a softmax or logistic regression model. But there are pros and cons for both. Basically, as I mentioned, generative classification has this nice property that it can leverage unlabeled data. It can do semi-supervised classification, right? So there are certain regimes where generative classification outperforms discriminative classification. Yeah, so it depends on what, there's no single universal good model, right? You can always, in certain regimes, one model outperforms the other, in certain other, the other one, okay? Yeah, so let's move on to latent variable models. So what are latent variable models? Well, so far our discussion has been limited to the setting where we have some data that we observe. The data is coming from some probability distribution, okay, that is defined by some parameters theta, right? So the models we were generating some data, the very first lecture, generating some examples using some Gaussian distribution and then estimating the parameter of the Gaussian. Or linear regression, where we are modeling a y conditioned on the parameter, the weight vector. I'm using theta here, which is basically the W weight vector, right? And the data, input x. We also saw the generative classification, which is basically very similar to this setting, except that you also have some x being modeled, where x will be also parameterized by some other distribution. But that's all that you have in these models. You have some data and some parameters. Okay. that need to be estimated. So our discussion so far has been on models that looked like this. On the other hand, there is a wide variety of there are a wide variety of models that also consist of variables that are known as latent variables. Okay, so the model. So I've shown you some examples here. So let's consider a mixture, a clustering problem. Okay, in clustering problem, you observe some data, but with every data point, there is an associated latent cluster that the data point belongs to. You don't observe the identity of the cluster. You only observe the data points. Okay? So the cluster IDs are like labels, right? But they are not, they're hidden from us. Okay? So in some sense, they are latent, right? They are basically latent, right? So we can treat these kind of variables as latent variables, and then the problem becomes of estimating the parameters as well as latent variables, right? So the very first picture that I've shown, the leftmost figure here, so we are trying to model some data, but with every data point, we also have a latent variable, okay? Now, depending on the problem and application, this latent variable can have different meanings. In the clustering example, this latent variable will be simply the class ID or the cluster ID, okay? And then, of course, there will be other parameters that define the model, right? So this is like a unsupervised learning problem using a latent variable model. The figure in the middle is a model for supervised learning where we are trying to predict Y. Okay, we have a X and Y pair. Here also, we can assume that the data has some other representation given by Z. So rather than predicting Y from X, we are predicting Y from Z, right? Where Z is some latent or hidden representation that we can learn. So you can think of, so I guess you have seen principal component analysis, right? So where the idea is that we have some high dimensional data and we reduce the data dimensionality to some lower dimensional space, to some small dimensional vector, right? And so what you can think of this Z here in this particular picture is some compressed version of the data, right? So X may be high dimensional, let's say a high dimensional image, pixel vector of pixel intensities, and Z may be some compressed version of the same image. And rather than using the actual raw image, we are using that compressed representation to predict Y. Okay, so this model kind of captures that. So it's a latent variable model for doing supervised learning, where instead of learning to predict Y from X, we are learning to predict it from the Z. Okay. There are also like sequential versions of these models where we can actually have a data that arrives in a sequence like X1, X2 up to XT. Right? Or suppose you have a sentence, right, where you have a sequence of words, and we are trying to assign each word a part of speech tag. Okay, so we observe words, but we don't know what the part of speech tags are. We may have to predict those tags. Okay, so the data is inherently sequential, and so are the tags, right? So we can assume that there is an underlying model where the tags are generating the words. So tags are also like cluster IDs. So suppose there are 10 type of tags. So there are 10 type of clusters. Each word belongs to one of the clusters. And the cluster that it belongs to is basically the tag of that word. So in this problem, actually, as you can see, the latent variables of the successive observations are connected. They are related with each other. So this is a classic example. This is one of the this kind of example is very common in things like hidden Markov models. HMMs, right? So you have a sequence of latent variables and that are generating observations. Okay, so as I was saying, in all these cases, the Zn here, that with every observation we have a Zn latent variable, the meaning of which will depend on the kind of problem and application that we have. But in each case, the latent variable is some sort of a hidden or latent representation of the data that we are modeling. Okay, we will look at some examples shortly. Yeah, so let's look at a motivating example, and that example is basically the so-called very well-known mixture model for data. Okay, so again, so suppose in this case we have an unsupervised learning problem. We are given a bunch of observations x1 through xn, okay, and we assume that these observations are coming from a mixture of k distributions that are defined as p of x given theta 1. So theta 1 is the parameters defining the theta 1 denotes all the parameters defining the first distribution. Okay. Likewise, you have such k-such distribution. These distributions could be Gaussian, these could be Bernoulli, these could be Poisson, right? So depending on the model or the data, you can choose the appropriate distribution for these. And you can think of this problem as something like this, where you have, let's say in this case, it looks like the data comes from a mixture of 3 distributions. Okay. But we don't know which data point comes from which distribution, right? So even though we have like these three separate distributions, since we don't know which data point comes from which distribution, essentially all we have is this red, curve depicting the distribution. We don't know which data point belongs to which of these clusters. Okay, so it's a purely unsupervised learning problem. There are no labels associated with any of the data points. The labels are something that we have to infer from the data. Okay, so in order to estimate mixture models of these type, we typically assume that there is some. So as you can see, it's a mixture model, right? So there are k components in this mixture. We assume that every component contributes a certain fraction of data points. Okay, so let's say that each fraction, so the kth fraction computes pi k fraction. Kth component contributes pi k fraction of data points. So pi 1, pi 2 up to pi capital K, right? So overall the sum will be 1 because 1 is the total, the complete thing, and then pi 1 up to pi capital K are the fractions contributed by individual components. However, we don't usually know what the fractions are, right? Because we don't know which data point is coming from which mixture component. So usually we don't know. However, in some cases, someone might tell us that, well, you don't know which data point comes from which mixture component, but I kind of know that 20% come from one component, 30% from the other, and maybe 50% from the. But in general, we don't know this. We may have to estimate this from data as well. Okay, and as I said, this the mixture proportions sum to 1 over all values of small k. Okay, so in this mixture model, our task is to estimate what these distributions are, basically what the parameters of these distributions are, okay? And in order to do that, we also have to estimate which data point comes from which distribution, okay? So in order to do that, we pose this model as a latent variable model, and we associate with every data point xn another latent variable zn, which takes one of capital K many values. And the value of zn will tell you which component or which distribution generated x. Okay, so Zn takes one of capital K many values. So Zn is that latent variable. Okay, and if once we have this latent variable, we can actually think of a so-called generative story as to how this data might have been generated. Okay, so generative stories are very popular in probabilistic models where you have some data and you can kind of think about, okay, how this data came into being, how was this generated? So let's assume that there was some process that generated the data. Okay, so let's look at what a reasonable process might be for this kind of a data that is coming from a mixture model. Okay, so this process that we have for a mixture model looks something like this. So we repeat this process for generation of every data point, x1 through xn. So what we do is that in order to generate the data point, we first need to know which of the k distributions has generated them, right? So let's first kind of like choose which component is generating this observation, right? So let's first choose which of the k distributions is generating this observation xn. Okay, so in order to choose that, let's assume that this Zn is drawn from a multinolly or categorical distribution, which will give you one of the k possible values. Okay, so we first generate the cluster ID or the mixture component that is generating the data. Once we know that, then we know which of the k distributions to generate this xn from. Okay. So once we know that, then we can generate x from that mixture component. So if we know that Zn is like a particular value, let's say 3, then we'll go to P of x given theta 3. Okay? So it's a two-step process. We assume that Z is generated first, and then we generate x, conditioned on Z. Okay? So this is the generative story. Note that both steps of this so you have a distribution over Z, right? Z or Z, right? Multinolly with pi. So pi is the mixing proportions, right? So why are we drawing it from multinolly of Z given pi? Because pi is the mixing proportions, right? So if you have a priori, the component that has a larger proportion, in the mixture will be more likely to generate. So Z will be more likely to take that value. However, we don't know pi. So pi is another thing that we will have to estimate, right? But I'm just saying that if you know pi, then this is how You can think of Z being generated, and then once you know the Z, then you can go to the appropriate distribution and generate the data from that distribution. So this is kind of a reverse process. So this is not what we do when we learn from data, right? When we learn from data, we are given X, and we want to learn all the Z, pi, everything, right? But we are kind of reversing. We are kind of thinking about how the data was generated, right? So we can assume that, well, we first chose the label or cluster ID, and then we went to that cluster and generated the data from there, okay? So probabilistic modeling problems are often defined. The generative models are at least defined in this sense, that you generate this, that it's a very easy way of explaining how the data was generated, right? And then you can recover the parameters by doing parameter estimation. Okay, so this is the generative story, and the goal is, of course, that we are given this data x1 through xn. Our goal is to learn the k distributions, which basically means that we are estimating theta 1 through theta k and the latent variable. So we also have to estimate z1 through zn, z capital N. Question? Yes.
What was the estimation of p of x given theta set delta?
Yeah. So the thing is, we will estimate that, right? So as I mentioned, the goal is to learn the k distribution. So we will assume that p of x given theta is a Gaussian distribution with some parameter. Maybe Gaussian, maybe some other distribution. The parameter is not known. Theta is not known. Yeah, so theta is what we will estimate from the learning procedure. So we will have a learning procedure that will allow us to estimate theta. I'll talk about that procedure briefly. So none of these things is known. Neither is pi, neither pi nor theta. None of these is known. We are just describing the process, right? And then using that process to define the model, and then we'll learn the model.
Z is between 0 and 1?
No, so Z is between, it can take one of k possible values. So because there are k components, right? K mixture components. Each data point can belong to one of the k components. So Zn is the component that xn belongs to. Of course, Zn is not known, but it can only take one of the k possible values. So it's not between 0 and 1, it's between it's 1, 2, 3 up to k, one of the k, which is why it's drawn from a multi-Nolly distribution. So multi-Nolly is basically a discrete distribution which gives you one of the k possibilities. Okay? It's also known as multinomial with just one trial. So multi-Nolly is a special case of multinomial. Okay? So as I was saying, if each of these distributions, p of x given theta k is a Gaussian, then it leads to the so-called Gaussian mixture model. Okay? You might have heard about Gaussian mixture models. You probably might have a lab on Gaussian mixture models. We will look at Gaussian mixture models in briefly. We will not get into all the technical details. We will not be able to in just a single lecture. But the basic idea is that Gaussian mixture models are a type of mixture models where each component is a Gaussian defined by a mean and a covariance matrix. Okay. Any questions on mixture models? Okay. Yes.
So you said getting Zn, multinomial of Z is given in pi.
Yes.
Won't it be every time giving the one pi which is the same Zn every time because which is most probable?
No, so the thing is, so by the way, this is just a notation. It basically means multi-Nolly pi. I'm just saying that Z because it's a distribution over Z. Okay. Now, so when you draw from, so pi is a vector of size k. So anytime you draw from a multi-Nolly, you'll get one of the k possibilities, right? Every time you do, so this is going in a for loop. For every x, you'll draw Z, right? So if you'll draw from a multi-Nolly, you'll get one, two, up to one of the k possible values, right? You repeat this for every data point. Once you know Z, you generate the data. You go to the next data point, you repeat the same thing, right? So it's not that you'll take the component of pi that has the largest value and it will be Z for every data point. It's a generative model. It's a random, you're drawing a random variable. All right? All right. So we have defined a mixture. So mixture model is a type of latent variable model where the latent variables are the cluster indicators. They are not known, so our goal is to infer those latent variables, the Z's. Okay. So one of the nice things about, so we are talking about mixture models and Gaussian mixture models. So you must have already seen k-means algorithm for clustering, right? So Gaussian mixture model also allows to do clustering because once we can learn Z, we have clusters, right? We have identified the clusters. So how is it different from k-means? Yes, yeah. So as someone said, k-means only provides a hard assignment. So it will only assign a point to a single cluster. It has no way of predicting like the probability that a point belongs to each of the k cluster. Whereas in a Gaussian mixture model, because as you can see in this picture, clusters can be overlapping, right? So what would you say about the cluster assignment for this overlapping region? So if a point belongs to this overlapping region, there's always a very large, big ambiguity, right? So rather than saying that a point deterministically belongs to one of the clusters, maybe just say that, well, there's a 30% probability that it belongs to one cluster, 70% probability that it belongs to the other cluster, right? So using a Gaussian mixture model, you can do this soft assignment, okay? Now, that is not to say that you can't do soft assignment using k-means. Even with k-means, you can actually look at the distances from every cluster, and you can sort of do a fuzzy assignment. So there's something like fuzzy k-means which can do that. But Gaussian mixture models have a lot of other nice properties that they can be formulated as Bayesian models. You can do prior distribution. All sorts of things can be done. So it's a more rigorous or more principled way of doing soft clustering as opposed to fuzzy k-means. Okay, so how do we learn mixture models, right? So what is the goal here? What are the things that we are trying to learn? So as I mentioned, in a mixture model, you have to learn the z1 through zn, and the theta1 through theta k, the parameters of the distributions, the cluster indicators, and I think I forgot, but you also have to learn pi, right? So pi, okay, so you have to learn the mixing proportions, you have to learn the parameters of all the k distributions, and you have to learn the cluster assignments of all the points. So these are the unknowns of the model that you have to learn if you're learning a mixture model. Okay, so for example, if you look at this leftmost picture, you have z and then you have the theta. So theta is basically all the thetas along with the pi. So this theta subsumes everything. I've just used a very compact notation. So how do we learn theta and z here? Okay. So suppose right now we only care about theta. So suppose we don't care about, okay, so this is a mixture model. Now let's say that we don't care about the cluster assignments. We only care about learning what are the mixing proportions and what are the mean and covariances of every Gaussian, or what are the, so we just want to learn the distributions. And we want to learn what fraction of data points are coming from each distribution. Okay, so suppose we ignore this for the time being. Okay, can we solve that problem? Okay. Okay, so let's see whether we can solve that problem. Okay, so so in this picture, suppose we don't care about z, we only care about theta. Well, one option would be to do MLE or map, right? So the basic approach. So how would we solve an MLE or map problem for this case? Well, so let's say all the parameters except z are denoted as theta. Okay. So theta hat will be arg, so this is the log maximum likelihood estimation. Argmax log of p of x given theta. This is what we do when we do MLE, right? In map, we have log of prior as well, but let's keep things simple and let's look at the MLE formulation. So this is what we would like to do if we want to do learn just the theta. However, in this model, we also have z, right? So we can't directly say that in order to get p of x given theta, we must look at, we must sum over all possibilities of z because we don't know z, right? So using the sum rule of probability, p of x given theta can be written as the joint probability of p of x comma z given theta with z all possibilities of z summed over, right? Right? If z is continuous, then we have to use an integration here. But we have to either use a summation or an integration here in order to do this because, okay, so we have log of sum of this quantity, right? Now, if we can do this, then we can do MLE for theta, right? However, this problem is no longer easy. So if you recall, the MLE problem for Gaussian mean estimation was fairly easy. We could get a very simple, closed form expression, right? Same for the linear regression model also. We could just get a least square like objective. But here, because in order to do MLE, we have to sum over all possibilities of z, and there are just too many possibilities of z, right? If you have n data points, each data point belongs to k many, can belong to k, one of the k possibilities. So you have like k to the power n many possibilities to sum over, right? And it also doesn't have this very nice structure that you have a log followed by summation, right? So even algebraically, it's not a very convenient, problem to solve. Okay, because if you have n data points, then typically you have the product of the log of this product over all the n data points, right? But here you can't really take the log inside the summation. So just doing MLE for this problem is not very easy, okay? Because z is not known. Okay. However, so how do we solve MLE for these kind of latent variable models where we also have z? Well, one option and one very popular option is to follow an alternating scheme where you estimate z assuming that theta is known and then estimate theta assuming z is known. Okay? Because if I know, so if you look at this problem, if I know Z, then I don't have to do this summation over all possibilities. Because because suppose, you know, in the clustering problem, if I know Z, then I know the cluster that, you know, each data point belongs to. Okay? Then estimating the distributions becomes the generative classification problem. Right? It's very easy, right? So if I know the cluster ID of every data point, then it becomes generative classification. I want to connect it with the generative classification, because then I know, okay, these points belong to this mixture component, these points belong to this mixture component. All I have to do is basically solve a density estimation, P of X given Y, right? So knowing Z, estimating theta is trivial. Trivial as in like it's almost as hard or as easy as generative classification, right? Likewise, if I know theta, we can even estimate Z. So knowing theta, we can estimate Z. How? Again, intuition. I will just like, I don't have any questions on the slide, but I'll just give you an intuitive meaning or intuitive reason. So suppose I know what each of the distributions are. Suppose I know theta, then I know what the k distributions are. Okay? And suppose I want to compute Z, the cluster ID of any data point. What I can do, I can compute the probability of this data point under each of the k Gaussians. I know, right? And whichever data point, whichever Gaussian gives me the largest probability, that will be the cluster ID. That will give me the cluster ID, right? So knowing one, the estimation of the other becomes fairly easy. Okay, which is why problems of this type, where you have both latent variables along with some other parameters, they are typically solved in this alternating scheme, where you estimate, let's say Z given you assume that Z has some, let's say we have a reasonable guess of Z, right? Using that guess, we can estimate theta. Likewise, with the new estimate of theta, we can improve our guess of Z, right? So it's guessing and refining kind of a iterative procedure that you can do. And something like k-means, k-means also has the same flavor. You make an initial guess of the cluster center, and then you try to find the cluster assignments. And then once you have the new cluster assignments, you recompute the cluster means, right? And you iterate, right? So it's same kind of a thing going on here also, but in the more sophisticated probabilistic setup. But again, rather than getting into the technicalities, it's important that we get the basic intuition that this is not very different, from those alternating schemes like k-means. Okay, so you do this, you keep doing this until you converge. Okay, and one of the very popular algorithms known as expectation maximization, or EM, it basically works in this fashion. So EM is a very popular algorithm for doing parameter estimation in models where we have such latent variables. So if we have data with latent variables with every data point, then EM is basically a scheme which basically operates in this fashion, where we have. So it basically has two steps, an expectation step and a maximization step. Expectation step basically estimates Z or a posterior distribution over Z, and the maximization step basically solves an MLE problem on the parameters, assuming that Z is known. Okay, so it's a very like a simple two-stage procedure that gives you the estimates of the parameters. So something like a Gaussian mixture model, if you want to learn a Gaussian mixture model, you have to use this expectation maximization algorithm. Okay, but the basic idea is this alternating scheme, where what you do, you assume that the pi and the theta1 up to theta k, they are known, they are initialized to some value, and then based on that you estimate Z. I think I have the algorithm on the next slide. Yeah, so yeah, let me just show you the basic algorithm.